welcome people to the Monday seminar and thank Stefania for putting together a fabulous talk. We are going to hear it and have a chance to discuss. For those of you who are new to the seminar, our normal mode of operation is to ask you to mute yourself, but to encourage you to interrupt with points of clarification along the way. And then there'll be an extended period at the end for, let's say, more detailed, complicated, interesting questions and discussion at the end. So, and that I will encourage everyone to participate in. The seminar is open to everyone. It is open to young, early career scientists and everyone else. And we really want to encourage early career people to participate in the discussion. So I will say no more, except for to thank Stefania once again and to turn things over to her.
Thank you, Chris, for having me. I will make this small, okay. So today we will talk about nonlinear elasticity, earthquake triggering, and seasonal hydrological forcing along the Irpinia fault in southern Italy. And these activities were part of the project MyBURP, which stands for Modulation of Hydrology on Stress Build-up on the Irpinia Fault. And it was a collaboration from the National Institute of Geophysics and Volcanology and the University of Padua, University of Naples, and Acquedotto Pugliese. So just an overview of what we will talk about. We will see an introduction and we will talk about nonlinear elasticity. Then we will make a focus on the steady area and on the hydrological forcing. And then we will move on results and we will see the seismic velocity change estimated from Kodaway interferometry of ambient noise, the strain sensitivity of velocity change, and we will see the correlation between the seismicity rate and the strain and the seismicity rate and seismic velocity variation. So let's start from the introduction. With the linear elasticity, we can explain a lot of seismological observation, and the ideal elastic behavior is defined as having a unique single value function between the stress and strain, ignoring hysteresis or memory effect, and an instantaneous response between stress and strain, and a linear relationship between stress and strain. And we can describe, for example, the propagation of the wave field propagating from seismic source at the time scale of earthquakes and, for example, in far field approximation. But the behavior of geomaterials can be much more complex. And, for example, rocks can behave in a nonlinear manner. So, for example, rocks can be modeled as a matrix containing some elements like cracks, intergrain contact, and the contribution of these elements to the macroscopic stress-strain relationship can be activated or deactivated because of change in the loading or some fluctuation in the temperature. And so when we want to describe the real behavior of geomaterials, we need to move from the linear elasticity to the non-linear elasticity, at least at the first order, to include the possibility of velocity change because of any change of the strain. And scientists developed an ad hoc laboratory experiment named pump probe experiment, in which they measured the velocity change estimated from the green function, which is the probe, and excited by loading or unloading of man-made strains, which is the pump. And actually, in the laboratory, this can be easily performed. You can control the loading, but they exported this kind of experiment also in a natural environment. Still, they could use some man-made strains, but also they started to use also natural sources like half tides, and they could export this kind of experiment also in the natural environment, thanks also to the advent of ambient noise. Thanks to that, they could measure the green function, for example. So similar to this kind of experiment, we want to use a natural source, which is, for example, the seasonal hydrological strains as the pump, and with object to investigate the elastic nonlinearity of crustal rocks and its role in seismic failure along the tectonical active zone of the Irpinia fault system. So in the Apennines, we are in extensional, we have an extensional deformation, and here with the color code we have the interseismic deformation, which is significant in this zone. And actually, what is also peculiar of Apennines, it's the hydrological forcing, which is characteristics where we have karst systems which are hosted generally where we have shallow carbonates that are highlighted here by this green patch. So in this box where we are focusing, we have both contribution, the interseismic deformation and the hydrological forcing. And actually we want to explore the interaction between the interseismic extensional deformation and the hydrological seasonal deformation linked to the phase of charge and discharge of karst springs related to the change of the height of groundwater table. So I know all of you know that a seismogram recorded at the seismometers, for example, of an earthquake, it's just the convolution of three terms: the source function, of course, the instrumental response, and here there is the green function, which is describing the propagation of waves from, for example, the hypocenter to the seismometers, and it contains information of the elastic properties, and in our case, it's the probe. So in seismic interferometry, we have so many energy sources, like noisy sources, and there is a boundary surrounding all these energy sources. And we can imagine to have two receivers inside inside the region surrounded by this boundary. And the wave field propagating from each source, it's of course propagating inside this region. And the signal cross-correlated between these two receivers, if we stack all the signals, we have that the energy traveled between these two receivers will be added constructively. And the resulting cross-correlated signal will approximate the green function between these two receivers, and it will be like the seismogram from one virtual source located in this receiver and recorded in this second receiver. In the case of random noise, there is a surface surrounding all these noise sources, and the source can act all together or in overlapping time. So the recorded signal and the receiver, it's already summed together. And we have that the cross-correlated signal between these two receivers is approximated the inter-receiver green function if we satisfy three conditions. First, the noisy sources should be independent each other. Second, the surface should be far enough from the two receivers, and the noise should be recorded for a sufficiently long time period. And here an example of a waveform recorded, for the green function obtained from a real earthquake, and the green function obtained from ambient noise. So there was this earthquake in 2007, recording occurred in Folkestone and recorded at this seismic station in CWF. And then they installed a second station very near the epicenter to monitor the aftershock sequence. And here the comparison of the green function of relay waves obtained from the earthquake, and here the green function obtained from the cross-correlation of the signal between these two stations for the 3 successive months successive to the occurrence of the earthquake. And when we superimpose the two waveforms, they look very similar. And so we can obtain real seismogram just from virtual energy sources using recording of background ambient noise. So in that case, we were talking about ambient noise. Now we will move on coda wave interferometry, and actually coda wave interferometry can be related not only to ambient noise, but also to the coda of earthquakes. So the coda of seismic waves, it's just that part of signal related to that it's after the arrival of direct phases. And in a medium strongly heterogeneous, the coda is dominated by waves which have repeatedly sampled the medium. And actually, it's thanks to this repeated sampling that waves will perform a longer path paths, and small change in the medium will be amplified. So here an example of a direct wave, and here actually two examples of repeated sampling. In this case, for example, we have some scatters and the waves are with multiple scattering. And for a homogeneous velocity change in the medium and fixed location of scatters and then a changed path, we have that at the first order, velocity change can be obtained from change of the arrival times. And actually, with the coda waves, we can monitor elastic properties because coda waves carry information about the structure of the medium, useful to infer change of seismic wave velocity, like, for example, those occurring because of a change of applied pressure. So here an example from laboratory in which you can introduce controlled change over the time. So there is a sandstone block placed in an hydraulic press, and a uniaxial load is applied. And of course, there are some pressure sensors. And here the waveforms for two different pressure. And when we move on the coda, we see that the two waveforms are very similar, just there is a temporal shift. And the tick curve is for 6 megapascal, while when we increase the pressure, so for 8 megapascal, the curve is the thin one. So we have that when we increase the pressure, seismic velocity increase, and the propagation time decrease, so the arrival times will be anticipated. And with the coda wave interferometry of ambient noise, there are so many applications thanks to the fact that they can monitor elastic properties. So, for example, there is this application in California in which actually they measured the velocity change with the coda wave interferometry of ambient noise using seismogram arrays. And they measured the velocity change for a time period of about 20 years, and they saw that the velocity change are actually matching the hydraulic heat of the aquifer. So with the coda wave interferometry of ambient noise, actually you can monitor aquifer, and this is a cost-effective method to do that. So the message here is that you can monitor elastic properties, and you can have so many applications. And so now let's move on to strain sensitivity of velocity change. So here you have the relationship between stress and strain, where sigma is the stress, m it's the elastic moduli, and epsilon it's the strain, and beta it's our strain sensitivity of velocity change, which represent the second order quadratic coefficient of this relationship. And this is a function of strain rate, which can be related to, for example, aesthetic components. And at the first order, not considering aesthetic components, we can obtain the strain sensitivity thanks to this relationship. And so the strain sensitivity of velocity change is the proportionality between the applied strain and the velocity change we observe. In the case of the linear elasticity, this beta will be 0, and we will not observe change in velocity change. But as this value depart from 0, the nonlinear elasticity become more significant. And what it's observed is that velocity change are actually anti-correlated respect the strain. So we have decrease during dilatation episode or increase during contraction episode. So the strain sensitivity can have negative value, and the fact that can have negative value, it has been explained saying that the velocity change we observe, they may be related to closing or openings of a crack because of the strain. So here an example in which they measured the nonlinear elasticity using a natural source like the half tides. So they saw that there are systematic velocity variation in response to tidal deformation recorded by a dense array in Southern California. And here you have areal strain, and here a focus of the amplitude recorded by one station. And they saw that actually velocity change and areal strain are anti-correlated. So you have this negative slope, and the strain sensitivity, it's in the order of 10 power 3. In this case, they were working in the frequency range 2 8 Hz, and they were focusing in the first meters of the crust. Actually, the range for strain sensitivity coming from laboratory experiment and other measurement on the field is always negative and going from 10 power 3 to 10 power 5. Also, there is this other work in laboratory in which they studied the nonlinearity of a sample with a single crack. Actually, they saw two kinds of sample, one with a more roughness crack and one with a worn, more smooth crack. So let's focus before on one sample, and we can see that when we move from the intact area to the cracked zone, the nonlinearity is increasing. You can see that the slope is increasing. And when we compare these two kinds of sample, actually, the nonlinearity is increasing for worn material. This is because it requires a lower level of external stress to open the crack and to show nonlinearity. And we said that velocity change that can actually, monitoring velocity change, we can actually monitor elastic properties. But the temporal change of seismic velocity during the earthquake cycle have the potential also to illuminate physical processes associated to the fault weakening. So here two work from Tinti and from Scuderi, in which they performed some laboratory measurement. And in this first case, they compared some laboratory experiment with the slow earthquakes. And in this second paper, they compared the slow and fast earthquakes with the laboratory experiment. And actually, especially in this last paper, what they see is that there are some systematic variation of elastic properties during the seismic cycle for both slow and fast earthquakes, indicating that there is a similar mechanism during rupture nucleation. And also they observe some decrease in seismic wave velocity before then the rupture. So maybe asperity contact within the fault zone began to fail before the macroscopic frictional sliding. So it's very important for sure to monitor the change of elastic properties. So now I will move on the region that was of our interest. So about the seismicity, okay, this region is for sure famous for the earthquake occurred in 1980. It's the strongest instrumental recorded earthquake in Italy till now. It was 6.9 surface magnitude. But recently we observe only microseismicity. These are the reference for our time period that it's between 2008 2022, but till now it's still microseismicity, and it's actually a diffuse microseismicity. The earthquakes are occurring at all depth, but they can accumulate. The most of the earthquake can occur at 8 to 12 kilometers of depth. And we said that this region, we have a significant action of the interseismic deformation, but also that we have this region, in this region we have also significant hydrological forcing. And here you can see the green patch that it's for the shallow carbonates, and here you have the aquifer that it's hosted in Picentini Mountains, which is releasing its groundwater through the Capusile Spring. And actually, these karst systems are very peculiar, and their structure is very peculiar. And in Apennines, in fact, karst systems are diffuse fracturated system. And we have that the channel of rainfall and also of melt snow can increase the hydraulic heat of the groundwater. So we have this groundwater table that is recharged during when we have this rainfall during winter, for example. And so let's try to characterize the aquifer that it's hosted in the Picentini Mountains. So here you have discharge time series in the time. And the first observation is that we have this peak during summer. And actually this shape is very smooth. It's not answering to individual rainfall events. And also when we have dry period, actually the hydrograph, it's never zero. It's just, you don't have the peak, but and it's flat, but it's never zero. I said that it's not answering to individual rainfall events. In fact, it's like the shape of a discharge. It's like smooth respect to time series of rain and also delayed in the time. So, for example, we have that the peak of precipitation, it's during winter in the months between November and January. And the peak of discharge, it's during May, July, so delayed of 4 or 5 months, respect the peak of precipitation. So this aquifer, it's accumulating the rain and the melting of snow. And in summer, we have the maximum of the discharge, which is a proxy of the hydraulic heat inside the aquifer. And what they saw previously analyzing the GPS component in Apennines, to which they removed, for example, the tectonic trend, they see that there are some transient signal, and actually this transient signal correlate with the time series of the discharge of the Capocere spring. And in fact, charge-discharge phases of karst aquifer can induce significant seasonal and multi-annual. So you have seasonal, but also multi-annual strain transient that modulate the tectonic extensional deformation. And the interesting point is that also this deformation is mostly horizontal and it's also anisotropic. In fact, here you can see again the GPS component to which they removed the tectonic trend. And in the first column, you can see the component rotated perpendicular to the Apennines direction. In this case, in the central panel, it's parallel to Apennines direction. And here you have the vertical component. And also, when you move from bottom to top, you are moving from Tyrrhenian coast to Adriatic coast. And so in the middle, you are looking to waveform, time series related to the Apennines. And you can see that actually these significant transients are visible perpendicular to the Apennines, are absent parallel to Apennines, and are negligible on the vertical component. So this gives you also the orientation of this forcing. And also they saw that not only the deformation is modulated by the phase of a charge and discharge of the karst aquifer, but also the seismicity. When they look to the background seismicity and they remove it and they consider it just the event above the completed magnitudes of the catalog, they can see that actually there is a modulation of also this background seismicity with some peaks of seismicity during summer. So the hydrological forcing is not only affecting the deformation, but it can modulate also the seismicity. So in this work, they also try to see if there is any delay between the change in time series of Capocere spring, that it's a proxy for the hydraulic heat, and the seismicity. In particular, they divided two layers of depth. So they're considering the shallow seismicity in the first 6 kilometers and the deeper seismicity between 6 and 12 kilometers. And they saw any delay between these two signals. And actually, for the shallow layer, the lag time is almost 0, so they are in phase. And the lag time for this deeper part, it's actually 2 months. So the question they tried to answer was if there can be a pore pressure diffusion that can trigger seismicity in the deeper part. But considering this lag time, the diffusivity coefficient should be greater than 10 meters square per second. That it's already an upper range for this kind of observation. So more than pore pressure diffusion, probably there is an elastic response, a poroelastic response of the upper layer, which is expanding when it's increasing the hydraulic heat. And the deeper layer, it's elastically coupled and maybe it's expanding also. So we have this further dilatation during summer, and we are in an extensional regime. So we have this further dilatation in the first layer, and this is interesting also the deeper layer.
Stefania,
So just see.
sorry, Sorry, it's Chris. Just want to, it's super interesting data. I should have asked this a few minutes ago, but now I have to. The hydrologic forcing you're showing us, the rainfall, it is it localized? Like what is the footprint of the region like where you're taking
Actually,
data
okay,
from?
yeah, it should be not localized, but so this time series, it's referring to this zone. So it's the Caposele Spring. Sorry, it's the discharge of this
The
Caposele
whole
Spring.
box.
That it's where the water of this aquifer is released. But we will see hydrological forcing. It's not related only this only here, but it's happening where we have these shallow carbonates which host aquifer. So they host karst aquifers, and so we will see that it's not only related to this region, but these measurements are related to the release of groundwater for this aquifer.
Okay.
But there are
Thank you.
other also, for example, in near Matese, in which they saw also other time series of the discharge, and yeah.
Okay.
So
Yeah, we can come back to it. Thank you. I see. Thank you.
okay, so just a brief summary. So velocity change describe change in elastic properties, and we can monitor them with the Coda wave interferometry of ambient noise, for example. And in Apennines, the hydrological forcing can induce significant seasonal multi-annual strain transient. So we saw in Southern Apennines, but it's a characteristics of Apennines. And in Irpinia, where we have the interaction between the interseismic deformation and the seasonal hydrological deformation, also, the background microseismicity appears to be modulated by the seasonal and multi-annual phases of groundwater recharge of the karst aquifers. So now I will move on our analysis and so on the results. So what we did here is we measured the velocity change of seismic waves with the Coda wave interferometry of ambient noise, and we performed autocorrelation of a continuous recorded of ambient noise. So here you can see the autocorrelation in the time, and here it's the stack for the whole period. That is for us the reference. And this is actually the example for the vertical component, but of course we did for all the components. And what we do is we measure the velocity change in this lapse time between all the days, respect the reference. And we do thanks the stretching technique, which is providing you also the correlation coefficient between your waveform and the reference. So in the end, you have like also a quality check, but also we use this coefficient to have a mean weighted by this coefficient for all the three components. And in the end, we obtain so the time series of velocity change in the time, and they are relative velocity change. So what we are looking here is, for example, here you have some negative relative velocity change. So it means that we have slower velocity respect the mean value, that it's the value that you observe in the whole period. And of course, when you increase the velocity change, you have like faster seismic wave velocity. And of course, the sensitivity of Coda waves is depending on the depth. So you don't have the same sensitivity with the depth, but we have that from numerical simulation. We know that the sensitivity of Coda waves is a combination of the sensitivity of body waves and surface waves. And also we know still from the simulation that when we move in late portion of Coda, the contribution of body waves is becoming more important, and the contribution of surface waves is decreasing. So here you have the velocity model, the distribution of events with the depth, and the sensitivity kernel for the surface waves. For this sensitivity kernel, we are actually sensitive to the first kilometer of the crust, and so mostly to the fracturated carbonate rocks which are hosting the karst aquifer. But we know that we are in late portion of Coda, so we are sensitive to body waves also, and actually, when we look to the scattered body waves, the sensitivity kernel of scattered body waves, considering a 3D formulation, we see that we can be sensitive also to a deeper part of the crust respect the surface waves. So we cannot constrain the depth, but we can have contribution also of the deeper part. Okay, so we have GPS station in this region, and we can obtain the continuous time series of the deformation. Here the convention is that you have a positive value of deformation for dilatation and negative value for contraction. And here you have the time series of horizontal dilatation that is obtained from GPS component to which we remove the tectonic trend. And they are in the order of 10 power minus 6. And also you can see that the time series of the deformation that it's related to this point, it's very similar to time series of the discharge. In particular, if we focus on this frame, for example, in which we have this peak of the discharge, that I remind you, it's a proxy also for the hydraulic heat, we have dilatation because positive strains are for dilatation. And it's not related only on this point. You can see that actually the dilatation, it's interesting a wider area, and especially where we have these shallow carbonates. Opposite, when we have a lower value of the discharge, so minimum hydraulic heat, we have contraction. And again, it's interesting this wider area. So it's interesting also that this deformation, it has an orientation in the space. So when we still look to this frame, we see that, for example, the deformation here, it's oriented in the same way in both cases for dilatation and contraction. What it's just changing, it's the sign of your deformation. So it's like happening in the same axis. And so what we did here, we try to count the azimuth of extensional axis and compressional axis. To do that, we counted the axis of extensional axis when we are in dilatation, and we counted the azimuth of a compressional axis when we are in contraction. And we see that the peak actually it's in the same direction, like west-northwest. So we can observe a uniaxial strain fluctuation, and that we attribute to the anisotropic poroelastic response of the crust due to the hydrological forcing. And so it seems that these strains are hydrological related. We try to see also if it can make sense. Like we know, for example, from other aquifer, how much can be the change in the height of the hydraulic heat, and using some reference value for the elastic constants. We see, for example, that for a change in the water table between 20-40 meters, we can have some change in the strain in the order of 10 power minus 6, that is in the order of the change we observe in the strain. So we have this, we said that we have this hydrological related strain. So let's move on to seismic velocity variation. Okay, here you have again the time series of discharge. The red dots are the east component of the GPS. The green dots are instead the velocity change estimated from Kodawa interferometry, and the negative axis is toward up, just to make more easy the comparison of the similarity between these two signals. And this station is this MIS-CRV. So first comment is that we are looking the time series of two different instruments. So the GPS station and what is coming from the seismometers, and they are looking to the same phenomenon, and they are looking something very similar to the time series of discharge. And this station, it's actually on the carbonates and very near to the Capocele spring. And so we have a hydrological signature also in the velocity change. And actually, when we move to this other station that is still in the tectonically active deformed area, but outside carbonates and far from the Capocele spring, like 25 kilometers, we see velocity change that in amplitude are smaller, and actually we don't see any hydrological signature. It's like they have a flat response, So the hydrological signature, it's not so local, but for sure it's peculiar where we have these shallow carbonates. And so for our study of nonlinear elasticity using hydrological forcing as pump, we will focus on this station. So before we were looking to the GPS component, but to compare the signal, it's more useful to see the deformation and the time series of velocity change. Because of course dilatation is the deformation is telling us if we are in contraction or if we are in dilatation. Let's focus before on this first frame, in which we said we have a peak of discharge, we have dilatation, and what we observe is a decrease of seismic wave velocity, because the negative value are towards up. And so the deformation and velocity change are anti-correlated. So probably what we see here is that we have dilatation, we have decrease of seismic wave velocity, maybe because of opening of cracks, and opposite, when we have the decrease of discharge, we said we have contraction, and again, we found increasing of seismic wave velocity, so again, they are anti-correlated. And also, we can see that there is this correlation between the strain, the velocity change, and the seismicity rate. So the seismicity rate here, it's obtained with the clustered catalog, and again, looking to the events with magnitude above the completeness magnitude of the catalog. And we have this peak in summer when we have this decrease of seismic wave velocity, and we have further dilatation respect the dilatation of due to the tectonic extension. But there are some here in which we have a further increase of seismicity, like there is a more productive triggering. And it's actually happening when we have a wider change of the deformation and of the velocity change. And so here the message is that during summer, we have a further dilatation, we have decrease of seismic wave velocity, and we observe more seismicity. So the seismicity rate is increasing. So going back to the fact that we could see also the orientation of the deformation, and we also know that actually when we observe decrease or increase of seismic wave velocity, they can be related to the opening or closing of cracks. We can make the same exercise as we did for deformation, but using, for example, the time series of velocity change. In this case, we count the azimuth of extensional axis when we have decrease of seismic wave velocity, and we count the azimuth of a compressional axis when we have increase of seismic wave velocity. And again, we found the same peak. And this can help us also to understand in which direction we have the opening or closing of cracks. So these are the results of our previous analysis, but now we are trying to, we are extending our analysis also to other velocimetric stations available in the area. And again, we performed the seismic velocity variation measurement from the Kodawa interferometry of ambient noise. And here you can see the two frames. What you see is again this anti-correlation between the deformation and seismic velocity variation. And the most important thing is that when you see this dilatation, actually you see this decrease of seismic wave velocity, that it's wider. So it's interesting a wider region respect just this part. And during contraction, you have actually increase of seismic wave velocity. So this is telling us that the hydrological forcing is acting as a source of change in elastic properties at a regional scale. Here, the example of I divide some station from outside carbonates in which we don't see the hydrological signature, and inside carbonates instead, where we instead see the hydrological signature. So these are the stations related to the outside carbonates, and these are the stations related to the tar inside carbonates. So this is just preliminary results, but now we will move again to our previous analysis. So we said that we see some hydrological deformation, and we can use this hydrological deformation to see to try to quantify the nonlinear elasticity for the site of a MIS-CRV. So here you have the time series of velocity change versus strain, and the whole time series, so all the points all together. And what we see, it's of course the negative slope and a significant slope. So the strain sensitivity, it's in the order of 10 power 3. And we try to actually to see also for single years if we could recognize some patterns. So we are talking about seasonal recharge, but actually there are also some multi-annual phases. It's not only related to a seasonal cycle. There is also a multi-annual phases. And so we can have, for example, that the starting point of the cycle can be different. It's like the offset can change, but what is constant in all these year, it's the slope, that it's actually related to the strain sensitivity. And it's always in the same order. So we always observe this significant non-linearity for all the years. So we have this seasonal change in elastic moduli because of this external forcing and because of this volumetric deformation. And also we observe that also seismicity, it's seasonal, has this seasonal behavior. So we can think about that maybe this change in elastic moduli can be in somehow related with the change in the seismicity rate. But also we know that we cannot constrain our velocity change, so we would expect that they are maybe related to the shallow crust, or maybe we are sensitive to a deeper crust. And so maybe the link can miss between this velocity change we observe and the seismic events. So it can seem that there is a missing part, but there are some independent study based on tomography. And of course, in the tomography, they have a better spatial resolution than us, but a lower temporal resolution. And in this work, they performed this tomography in the time, so for epoch, and they focused on two different volumes. Of course, we are in Irpinia, and a shallow volume for the first 5 kilometers and a deeper volume between 8 and 12 kilometers. And actually, they saw that the ratio of P-wave velocity and S-wave velocity for both volume, it's changing in the same way, and actually it's matching the multi-annual change of the discharge. So we have also independent studies that are telling us that the hydrological forcing is changing the elastic properties also in the deeper part where we have to the deeper part where we have the most of earthquakes and so at seismogenetic depth. So hydrological forcing is very significant. So now the question is, we have this time series, the deformation, the velocity change, the seismicity rate, and it seems that they are correlated because we have during summer this decrease of seismic wave velocity, the increase of earthquake rate, and during winter we have like, okay, it's not that we don't observe earthquakes, but they are surely happening less. So we want to see if there is any relationship between this time series, and we want to do with some statistical test. So we used quantile plot, where the quantile plot tests for a specific relationship between an external forcing and the seismicity rate, rather than simple asking if the earthquake's occurrence is correlated with such forcing. So here you have the classical quantile plot, and I will try to explain before this, then we will move to the modified quantile-quantile plot explained by Delori. So you can imagine to order your stress value or your strain value from the lower level to the upper level and count the number of earthquakes for a given value of stress or below that. And again, moving on and count again. So you can produce the normalized cumulative density function of earthquakes given a level of stress versus the time spent to observe that value of stress or strain. And if the earthquakes are Poissonian distributed, so are independent, respect this external forcing, you would have that actually they would stay on this curve that it's from 0, 0 to 1, 1, like they are just not caring about the external stress, so they would occur independently from that. And Delors suggests to modify this quantile-quantile plot, removing this trend in the way that you can emphasize any change respect this horizontal line. So in the case of Poissonian earthquake distributed, you would have just like they would be on the horizontal line. And he proposed also to build some, for example, synthetic catalog, adding an external forcing. So more and more you add this external forcing, your curves related to this synthetic catalog will depart from the horizontal line. And in particular, to explain this graph, it's like when you are moving from low value of strain to higher level of strain. So in this case, for example, contraction, you would have a deficit of earthquakes for that value of strain. But when you move increasing the strain, so when you move, for example, to dilatation, you would retrieve the earthquakes. In this case, so the earthquake rate and the external loading are positively correlated. He tried to reproduce also the case in which this curve is not symmetric, because it can happen that you can have, for example, some skewness, for example, towards right. And in this case, it's like the earthquake rate, it's proportional to the square stress. And this can be explained like you have like a threshold, a quasi-static threshold. And when you overcome this threshold, the triggering is more productive. So let's move on our case in which we made the same analysis of considering our catalog and the strain time series and our catalog of events, of course, and the velocity change. So they are two independent time series, and we should find something that is in agreement. And okay, so the red curve is for the real catalog, considering the strain, where here, again, the convention is that we are moving from low value of strain to higher value of strain, so from contraction to dilatation. And we have that for low value of strain, that is for contraction, we have a deficit of earthquakes. And we retrieve the earthquakes when we increase the strain, moving to dilatation. And this curve departs respect the Poissonian distribution of events. Also, we can try to quantify how much the external forcing is significant in the distribution of earthquakes. Like you take a percentage from the Poissonian distribution, and like you take 60% from the hydrological forcing. So randomly from the Poissonian distribution and 60% from the hydrological forcing. And we found in this case in which the seismicity rate is proportional to hydrological related strain in a linear relationship, that the contribution should be 60%. But we can see that there is like a right skewness. So we try to see also the relationship with the strain squared. In this case, the contribution would be 40%. So we have that seismicity rate and strain are positively correlated. And when we move to the increasing of dilatation, we found more earthquakes. So now we can see the analysis for velocity change. So in this case, we are increasing the velocity. So we are from slower velocity, seismic wave velocity, to moving to faster velocity. So we are increasing the seismic wave velocity. And in this case, we found an excess of earthquakes when we have lower value of seismic wave velocity. And the occurrence of earthquakes is decreasing when we increase seismic wave velocity. So in this case, they are negatively correlated, the seismicity rate and the seismic wave velocity. And it makes sense because actually we saw that velocity change and strain are negatively correlated. Also, we saw that there is like, again, this skewness, but this time it's left. So it's like, again, you have like a threshold. And when you overcome this threshold, the triggering it's like less productive when you increase the seismic wave velocity. So what it's telling us, this test, is for sure that also nonlinear variation of elastic properties are statistically correlated with the earthquake rate. So the question is, it can be related also with the triggering of earthquakes. So maybe this decrease of seismic wave velocity, it's related to the triggering, like it's more easy for earthquakes to happen when we observe this decrease of seismic wave velocity. And there is this paper by Johnson and Ja, I don't know the pronunciation, but they made some laboratory experiment in which they try to explain the triggering of earthquakes induced by large earthquake and at a remote distance, and also with small strains. And actually, the reason is that if you have a fault that is weak, you can have that seismic waves from large earthquakes can cause decrease in elastic moduli by break or loss of contact due to the vibration, and they can weaken furtherly. So if the fault is a ready near failure, this can induce fault slip. Of course, there are some characteristics required to observe this kind of triggering. So you must have a weak fault. You have to have a fault in a critical state, and also to have this decreasing of elastic moduli, you should have strain amplitude greater than about 10 power minus 6. So you need to satisfy this condition. In this case, if you are, you can have this kind of triggering because of also the nonlinearity response of the medium. And in our case, seasonal strains of about 10 power minus 6 are actually required for both the triggering, but also to observe this nonlinearity effect. So for this modulus reduction. So we are not saying that this is the reason, but maybe this can be an explanation. So in conclusion, we saw significant variation of elastic moduli in a tectonical active deformed area linked to hydrological deformation, and we observe nonlinear variation of elastic properties which are statistically correlated with the earthquake rate. And maybe the elastic nonlinearity for faults that are close to a critical state maybe can play a role in the earthquake triggering. This can be an alternative explanation respect the evolution of pore pressure or Coulomb stress. The triggering because of pore pressure or Coulomb stress. And okay, so here the references using this talk, and thank you for your attention. And if there are any question or if I can clarify better.
Stefania, that was fabulous. What a really nice talk. I will invite people to unmute themselves. Join me in thanking you for a great talk.